So Kim, our inbox has been blowing up with myths. People are going crazy. Do we have any good myths that we can look at really quick?
I bet we do. Let me look. Here's a really good one about solid core columns. And this customer is asking if it's true that solid core columns actually run at a lower back pressure than fully porous columns.
Yeah, I've heard that a lot. Obviously, solid core columns are becoming very popular. People are really kind of gravitating towards them. And one of the claims is that they run at a lower pressure. And that's obviously desirable because you can get two benefits. You can run faster, so get more done, or you can potentially run a longer column.
Get more resolution.
More efficiency.
Right, right.
So I can see why this would be important.
Yep. So I think maybe we should put this one to the test. We could, just to make it fun, let's focus on the sub 2 micron solid core columns.
Sure.
We can look at the 1.6 micron solid core.
Yep.
And we can look at a 1.7 micron fully porous.
Okay.
And really put this to the test.
Yeah, let's do it.
Okay.
So Kim, before we actually run any experiments or any columns, I dug into the literature and I pulled out the KozenyCarmine Equation, which I'm showing here.
Oh yeah, okay.
And what's really cool is that this equation dictates the pressure drop through a column. And one of the key characteristics of this equation, or one of the key attributes, is the d sub p, or the particle size. And as you change the particle size, that influences the pressure drop squared. And since we're using two different particle size columns, a 1.6 micron and a 1.7 micron, we would expect that 1.6 micron solid core column to have much more pressure than the 1.7 based on this formula.
All right, let's do the work and see what happens.
Sure.
All right, JT, we have some data. We ran the two different columns at different flow rates, and we tracked the back pressure, comparing the 1.6 micron solid core column and the 1.7 fully porous column. And what we see is that the pressure of the 1.7 and the 1.6 micron column are actually equivalent, which means that the solid core column has lower pressure.
Yeah, that's interesting, because again, based on the KozenyCarmine equation, since the 1.6 micron is a smaller particle size than the 1.7, it should have more pressure.
So let's figure out why.
Yeah, something weird's going on here. So Kim, to really understand, I think, what's going on here, we need to go back to that KozenyCarmine equation. We talked about particle size and the influence that has on pressure, but what we didn't talk about or really think too much about is the external porosity, or how tightly packed that column is.
Oh, different term.
Yeah, so if we look at the graph that's shown here, for a fully porous and a solid core column, the solid core column is packed to a much higher external porosity, and that equates to much lower back pressure.
Oh, I see.
Yeah, the fully porous column is packed to an external porosity of about 0.37, while the solid core column is packed to an external porosity of about 0.39. So now that we know that the external porosity and the particle size drastically influence the pressure, if you look at this graph, when we overlay the fully porous and the solid core columns, you can see now why they have equivalent pressure. So again, you take a little bit of a pressure hit going to the smaller particle, but because it's packed to a much higher external porosity, you get a benefit in pressure. So that's why they're equivalent.
Oh, very interesting. So JT, how do you want to call this myth?
Yeah, it's trusted. Solid core particles do provide lower back pressure when compared to fully porous particles, especially if they're of equivalent particle size.
Yep, so we should also mention, though, it really has nothing to do with the particle itself. It's more about, as we saw, how efficiently it's packed in to create a stable bed within the column.
Exactly right. Solid core columns you can pack at a little bit of a higher external porosity, and that's beneficial when it comes to pressure.
Absolutely. So let's write this up.
Okay.
If you'd like your question to be answered on a future episode, please feel free to email us at trustyourscience@waters.com.